So now that we've talked about how we can kind of get this value, this equilibrium constant, this K that tells us whether we are product or reactant favored when we reach equilibrium, we now can kind of start to think about a snapshot. At any given point in time in the reaction, where are we at? Are we there? Have we already reached equilibrium? Are we still getting towards equilibrium? Have we gotten too far past equilibrium? And that's where our next kind of letter of the alphabet comes in, and that is our reaction quotient. That's the symbol Q. Q is just telling us right at any given point in time where we are. The good news is it's the exact same math, the exact same setup as solving for K. We take our product concentrations raised to their exponents over our reactant concentrations raised to their exponents. And then that gives us, again, a unitless ratio number, which we can compare then to K. We say that if Q equals K, well, then we're at equilibrium. We've gotten as far to our products or reactants as we're going to get. And if we have continued change, we would no longer see a measurable difference because it is at dynamic equilibrium. But if Q is different, that actually starts to tell us a little something about where we are in the reaction and which direction our reaction is progressing. So if Q is less than K, if Q is less than K, then that means there are more reactants than expected. If we're thinking about our math, we've got products over reactants. If Q is too big, that means if Q is too little, it means we got too much in the denominator. And so we need to continue towards the product side, continue to the right, as we would say, to try to get to equilibrium. The reaction is headed to the right. If Q is if Q is greater than K, then the system is past equilibrium. We've got too many products and not enough reactants as we expect at equilibrium. And so we would actually see our reaction heading back towards the left, back towards the reactants. Typically, this can be done a couple different ways. We've kind of reached equilibrium and then we kind of alter or shift the equilibrium state, either by adding more adding more products, or we could be changing the pressure or the temperature, which then causes our reaction to then start to try to shift to undo that. Oh, the Chantelier's principle. And so if Q is greater than K, we're shifting back towards the left. And if Q equals K, boop, we're there. We've reached equilibrium and we are not going to see any further change in our substances. If we're looking at our reaction over here, kind of our example here, we've got our N2O4 was our reactant. We started with that. We didn't have any of that nitrogen dioxide to begin with. And at this first kind of chunk, this first block, Q would not equal K. At this point in time, we would have more reactants than products at equilibrium, or we would say that Q is less than K. As a result, we're going to continue making more and more products until we finally get to equilibrium, which is when our lines or slopes approach zero. Cool. A couple examples as we start to think about this. So let's just kind of start by writing some Q's. So if you would, go ahead, pause the video and write what the expression would be, the reaction quotient expression, products over reactants, see what you get. Hopefully you balance them. If you just threw all these up and put them all to the first power, we're going to be in trouble. You got to balance your reactions before you can write your Q. So we balance our first one here. We end up with 2, 4, and a 1 on the oxygen. So then when we take those and put those into our our reaction quotient expression, we would get something that looks like this. NO2 to the 4th times, that should be O2, sorry, a typo there, all over N2O5, our reactant raised to the 2nd. Those kind of coefficient values are now going to be our exponents for our expressions. We're assuming all of these to be elementary reactions. Cool. For the second one, once you got it balanced, we end up with this one, CO2 to the 3rd, H2O to the 4th, all over our C3H8, our propane to the 1st times O2 to the 5th. Cool. Hopefully this is layering in real easy. This should be pretty straightforward coming right out of your balanced equation. But if you want more examples, just let me know. Cool. So then we can actually use this. If we're thinking about our values, if you're more of a visual learner, if Q equals K, remember the C's here just mean equilibrium or our concentration values. If QC and KC, if our snapshot equals our equilibrium value, our equilibrium constant, well, then we're at equilibrium. No change is going to happen. If your Q is less than K, that means you got more reactants than products. And so your reaction is going to continue to react towards your product side to try to get those two to be equal and get us back to equilibrium. And if Q is greater than K, it means we got too many products, we got too much in the numerator. It's going to react then back to make more reactants to try to get it so that those two values are the same. We're always trying to get to equilibrium. And these kind of start to get shifted depending on how we see our Le Chatelet or where we are in the reaction. Cool. So for the reaction, let's take a look at one of these. For the reaction X plus Y2 turning to XY plus Y. Let me minimize for just a second so I can grab my screen here. Cool. So we want to actually, for each of the following scenes, I should get the question all the way up here. For each of the following scenes, if the KC, if the equilibrium constant for concentration is 2 at this particular temperature, which of the following scenes actually represents the mixture at equilibrium? I'm going to color code just a little bit here so that we don't get confused. So we said green is X, green is X, and our purple is our Y. Purple is our Y. Cool. Always, personally, I think you should always start by writing your equilibrium expression. So what is QC going to equal here if we're thinking about our reaction? Well, it's products over reactants. In this reaction, we've got XY. We got XY times our Y, which again is the purple one, our purple guys. That's going to all be over our reactants, which are going to be our X, our green guys, times our Y2, which is going to be our purple again. Cool. I'm just kind of color coding so we can kind of keep track of what's going on in our different beakers here. Cool. So sorry, all the same beaker, we're just different points in the reaction. So let's just kind of pull some numbers. Let's kind of count them up and see what we got. So here we've got, for thinking XY, we're looking for 1 purple and 1 green. So in the first box, I'm going to do the first box first. We got 1, 2, 3, 4, 5 of those XYs. So for box 1, we've got 5 of the XYs. We're looking now for our monatomic Ys. That's just lone purples. 1, 2, and 3 of those ones. That's all going to be over our X. Looks like there was 1 green floating around. And our Y2, there was 1 of those. Just make sure I've got all my particles here. 5 times 3 is 15. Divided by 1 is 15 for QC1. That is not equal to 2. Okay, well, that'll be important here. Let's hold that thought for just a second. Let's take a look at our second box. That was for box number 1, below 1 next to it, so we know which one that's for. For box 2, same QC, it's the same reaction. We just are at a different point in our reaction. So now we can kind of look, same process, different numbers. Our XY, we got 1, 2, 3, 4 of those. So for our new QC for box 2, we've got 4 of the XYs. For monatomic Ys, we've got 1, looks like 1 of those. Nope. There's another one. 2 floating around in there. Got 2 floating around there. For our lone X, we got 1, 2 there. And we need our diatomic Y, which is 2 and 2. So 2 there. We've got 8 over 4. 8 divided by 4 gives us 2. Ding, 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 ding. Looks like reaction 2 is at equilibrium, where our QC equals KC. We're at equilibrium for box number 2. Cool. Let's take a look at 3 real quick. I'm going to try to squeeze it on in here for our QC. We've got XY. We've got 1, 2, 3 XYs. We're looking for our monatomic Ys. We got 1 of those. For our monatomic X's, we've got 1, 2, and 3. And for our diatomic Ys, we've got 1, 2, and 3. Looks like we got 3 divided by 6, which is going to be 0.5 for our last one. Cool. So just think about if we're going to do the particle count and kind of get us a feel for where we are. If we're thinking about where we are for box 2, Q equals K. So for box 2, we are actually at equilibrium. Box 1, Q was greater than K. Well, what does that mean? It means your numerator is too much, right? You got too large of a value? Well, the numerator is the products. That means we have more products than reactants. We need to shift back to the left to try to get to equilibrium. Q is greater than K. For this last one, Q is less than K, meaning we've got too many reactants, not enough products. Q is less than K, meaning we're going to shift towards the product side for box 3 until box 1 and box 3 both look like box 2 at equilibrium. Cool. Kind of a particulate view. AP really likes to ask those types of questions, but we can also look at a mathematical type problem. Nope, that's the same box. Oh, it's all the answers. Got it. Yeah, cool. If we had some values, so for this particular reaction, we know the Kc to be 0.21 at 100 degrees Celsius. At a point during the reaction, N2O4 equals 0.12, and NO2 is 0.55. Is the reaction at equilibrium? If not, find out the direction. Well, we want to know if we're at equilibrium. Ooh, let me hit my button here. If we're at equilibrium, that means we're looking for a QC. Well, let's start with just the expression, products over reactants raised to their coefficients. Looks like our expression would be this value. Products of reactants, that kind of product's gonna get squared. I can plug in my numbers now. I've got 0.55 for my NO2. It's gonna be quantity squared over our N2O4, which was our 0.12. Ooh, I apologize. I didn't grab my calculator this morning as I was preparing for our video. Cool, so we've got 0.55 quantity squared divided by 0.12. That math works out to be 2.52 sig fig, so 2.5 looks like. Well, that QC is much, much greater than our K. Our K we know to be 0.21. Uh-oh, Pescadios. Uh-oh, Pescadios. If Q is greater than K, that means we've got too many products. This is going to be shifting back towards our reactants to try to get us to our equilibrium. Double check that with the answer key real quick. Make sure we're coming up with the right values. As good. So we're shifting back towards our reactants until we can get those values to be equal. Cool. Just a little practice with our Qs and kind of introducing this idea of the reaction quotient. Got some practice coming up heading your way as we continue to work through our AP Chem.